Now let me give the construction of the function u in the special case when the Lie group G is SLDR and the lattice gamma is SLDZ. First we let E1 through E sub D be the standard basis for RD. And we consider the following representation. Rho sub I from G to GL of the ith exterior power of RD. With each rho sub I given by rho sub I of G acting on a basis vector E sub K1 through E sub Ki equal to the wedge product of G acting on each of them. So here K sub 1, K sub I is contained in the set of 1, 2 through D. Now let's talk about a definition. Let delta be a lattice in RD. And we say that a subspace L of RD is delta rational if L intersection delta is a lattice in L. For example, so when D equals to 2, you have a lattice. So here is the lattice in R2. Then this L, this will be a legal delta rational subspace, but this one, this is not delta rational. And for delta rational subspace L of RD, we use the notation D sub delta of L, or we may omit this delta here. We use this notation to denote the volume of the lattice L intersection delta in L. Remember, this volume is defined in this way. If this lattice is spanned by the following vectors. Suppose this is a z-span of L in the intersection delta with the rank or dimension equal to L. And if tau is a linear transformation, of RD, let's send delta sub I to the standard basis vector E sub I, then the volume is given by the absolute value of the determinant of delta inverse. Now we introduce the following notation. So you consider all the delta rational subspace of dimension I. And you take the supremum of all the reciprocal of the discriminant of L with respect to the lattice delta. And we denote this supremum by of I of delta. For I greater than 0, greater than or equal to 0, less than or equal to D. So now we can give the definition for the head function. The head function is given as follows. For sufficiently small epsilon greater than 0 and delta greater than 0, it is a function given by the summation. It's a function of lattices given by the summation from I equal to 0 to I equal to D of epsilon raised to the power I times D minus I of I lambda delta. It can be shown that it satisfies the following two conditions. First of all, U sub lambda will go to infinity as lambda goes to infinity in G mod gamma. Remember, G mod gamma here is SLD or a mod SLDZ. So what do I mean when I say lambda goes to infinity? Well, there are two ways to explain this. First of all, you can put a metric here and pass this metric to this quotient. And lambda goes to infinity simply means the distance between lambda and the neutral point goes to infinity. Because this is remember, this is a non-compact space. That is one way to interpret this. Another way is by the so-called Mahler's criterion. This means for any small radius r, the intersection of this small ball at the origin and lambda always contains not just the origin. It's always strictly bigger than the singleton at the origin. Remember, so here, because this lambda always has a covolume 1, so every lattice here has a covolume 1. So in the Mahler's criterion, is the situation in the Mahler's criterion is equivalent to this. Otherwise, so in general, you need the boundedness on the covolumes of the sequence of lattices. So this is the first condition. The second one is the following. There exists constants C1 less than 1, B greater than 0, and a positive integer such that for any lambda in G mod gamma, we have the estimate the integration of this head function of the new lattice G acting on the lattice against the measure the nth convolution. This is less than or equal to C1 times U of x plus b. And hereby the nth convolution, I mean, this is a measure defined by the integration of the indicator function of A with G1 Gn d mu G1 d mu Gn. This is integrated over the product space. By Frobenius theorem, you can break this up into the iterated integration.